Should we start, sir?
Yes, sir. We can start, sir.
Okay, sir. Okay. So, Vishal, sir, please unmute yourself.
Sir.
Okay, sir. Okay.
So, shall we start, sir?
Sure.
Pardon? Shall we start, sir?
Yes, sir.
Okay.
Okay, start.
So, good morning, everyone. So, I hope my voice is audible. Screen is visible to all of you. So, first of all, thank you to Dr. Deva Prasad and the Dr. Sanjeev Agarwal, sir, for inviting me here to contribute to the success of this particular faculty development program. So, this session will be focusing on the wide area monitoring system for a smart grid. So over the next 1 hour, I will start from simple measurement to SCADA to VAMPs using the synchrophaser technology. And if time permits, we'll be discussing about something about the IEEE standard for the synchrophasers. So if we are talking about VAMPs, so VAMPs actually connects three key aspects. One is measurement, communication, and control. Together, they form the backbone of today's smart grid, to which we call actually wide area measurement system. Okay? For which we actually utilize the wide area measurement system. So can you tell me why do we all measure at all? So measurement is not just the technical activity, it is actually the part of our everyday existence too. For example, when we go to the market, you measure the weight to buy the fruits, vegetables. When we are traveling, we measure the distance, time. Similarly, when we are cooking something in our kitchen, we measure the quantities like sugar, salt, or water. So measurement is everywhere, but more importantly, why measurement is so essential? Because measurement it helps us to understand, communicate, compare, control the things in a fair and accurate way. So that's why the measurement is actually important. Let us now focus on why measurement are absolutely essential in our power systems. So if you look on these pictures, the first picture you will see a balance between the demand and the supply. So in any power system, generation must always match the demand. So if the demand is increasing but supply doesn't, so the system frequency drops below 50 hertz. So, and if supply exceeds the demand, the supply frequency rises. So we can say the system frequency is the key, or you can say the very first indicator of system health. So that's why the continuous measurement of frequency is critical. Similarly, if you observe the second picture, that is actually the energy meter. Meters are not just to billing the consumers, they are also important to record the consumption patterns, detect the theft, and provide the feedback to the utilities for system planning. So with the rise of smart meters, measurement now also support the demand response, and you can say the a dynamic tariff mechanism. Similarly, in the next diagram, you can observe the grid and microgrid. In modern power system, we no longer rely only on the centralized generation. We have microgrids with solar, wind, storage, and converters. So again, the measurement here plays an important role to manage the AC-DC interface, optimize the renewable integration, and maintaining the stability when it is grid connected or islanded. Similarly, this last figure, it shows the concept of demand response. Just a minute. It shows the concept of demand response because the demand actually fluctuates over the time. So sometimes it may exceed the available supply. So just by measurement, we can track these fluctuations in actual real time. So with this information, operators can implement demand response programs. They can reduce or shift the loads to balance the system. So hence we can say that the measurement actually the first key step towards the monitoring, control, and protection of any power system, of the entire power system. In power systems, we generally measure the four key quantities. One is voltage, to know the operating levels and check against the limits. Current, to identify the load flow and fault conditions. Power, both active, reactive power. Frequency again, it is a you can say the direct measure of balance between the generation and the demand. So without accurate measurements, operator would be practically blind. They will not be able to detect the disturbances. They cannot plan the corrective actions or ensure the grid stability. So they would have no idea whether the system is stable, overloaded, or about to collapse without the measurement. So this is the significance of measurement. So measurement system in microgrids, power grids fall broadly into two categories. One is the local measurement system. Second one is remote measurement system. So in local measurement system, where values are actually available at the local end only, at substations only. They are not actually communicated to remote locations. Whereas in case of remote measuring system, where the values are actually sent to the control center, they may be often hundreds of kilometers away. So traditionally, traditionally we have used SCADA for remote supervisory control. SCADA stands for the supervisory control and the data acquisition. This actually collects the data 2 to 10 seconds and is actually you can say suitable for the steady state operations and supervisory tasks. However, the SCADA is too slow for millisecond scale dynamics and it does not provide time synchronized angles. It only provides the magnitudes, not the angles actually, RMS values. So that is where wide area monitoring system, or you can say WAMS, comes in. So there we have written some functions of the SCADA. The first function is data acquisition, means it collects the information from sensors, CT, PTs, and meters through RTUs installed in the substation transmission lines and generating units. Second function, that is remote monitoring. Again, the operators at the control center, they can see they can have the information about the signals of different locations of the grid. They can see the status of equipments like breaker, transformers, and line conditions of the power system across the large geographical area on single screen. Next function is remote control. So by this function, the operators can send commands to command remotely to open or close the breakers. They can change the tap changer settings, or they can adjust the generation without actually being physically present there. So this saves the time, avoid the sending the staff on field physically. Next function, data storage and analysis. So SCADA actually also stores the all the major data for analysis purpose, for taking the corrective measures, for taking the decisions based on this analysis. This also helps in trend monitoring, forecasting the loads, and also for the future plannings, event and alarm management. So whenever there is some abnormal conditions occur, like overload, over voltage, frequency dip, SCADA generates some alarms. So this allows the operators to respond quickly before the things escalate, or it may go up to the blackout. So you can observe remote terminal units, they are installed in the substation and act as the local data collector. They actually gather the signals from sensors like voltage, current, breaker positions, and alarms. They then convert into digital form and send it forward. So all of these RTUs, you can see they are actually connected to some SCADA master station through a communication network. The communication here can be through the fiber optical, or previous technique power line carrier. So this ensures even remote stations can send their data to the central control room. Now, while SCADA has been extremely useful, it also has some serious limitations. The first one, you can observe the data update rate is very slow, in this case 2 to 10 seconds. So that is fine for the steady state monitoring, but it is far too slow for the fast dynamic events like oscillations or transient instability, which happens in milliseconds actually. Second, SCADA does not have global time synchronization. They actually rely on the local clocks. So each RTU has its own local clock. So when events occur at different stations, their timestamps may also mismatch. So this makes it difficult to analyze the wide area events accurately, because any small drift in the local clock may give you the wrong analysis. Third, SCADA mainly provides the RMS value of voltage and current. These values are good for the steady state, but not for the fault and the disturbances, where we require angles also, information of angles also. Fourth one, SCADA is suitable for monitoring and supervisory control, but not actually designed for the real-time fast decision making. This limitation is exactly what pushed the development of VAMs and synchrophasers. So all these are the limitations of SCADA. Because of that, we have moved towards the VAMs, or you can say the synchrophasers. So traditional electrical power system, for that SCADA was actually originally designed to monitor. In that case, only we have large generating stations located far away from cities and consumers. Power is transmitted over high transmission lines to the load center, and then finally it is distributed to consumers through distribution systems. So the traditional grid, it was built decade ago, and it was mostly unidirectional, or you can say one directional. Power flowed from the big generators through transmission lines and then to consumers. So SCADA system were designed for this type of traditional grid model. But today, with the renewable energy integration, distribution, generation, and bidirectional power flow, this old SCADA system is no longer sufficient. So the system dynamics have changed. Operators now need monitoring the system that can provide the real-time visibility and also need immediate response actions. So let's take a moment to see how the Indian power grid itself has evolved over the time. So in the early days, India did not have a single unified grid. Instead, it was actually divided into 5 separate regional grids, like northern regional grid, southern, eastern, western, and northeastern. So each of these regions operated more or less independently and sometimes even at different frequencies, different slightly deviation from the 50 hertz. But as the power demand grew and regional diversity in generation increased, it became necessary to interconnect all these grids because they actually improve the reliability, and by this way we can optimize our resources and we can also reduce the operating cost. So with the time, we have interconnected all the regional grids, and from that time, from that day onwards, India has had its one nation, one grid. But remember, with this national interconnection of all the regional grids, many challenges have also occurred, like a fault in one part of our country can now spread quickly to other regions. Local disturbances, they can escalate to large scale blackouts if not controlled immediately. In fact, this is exactly what happened in July 2012. So yes, I am talking about India's major blackout that happened in July 2012, and it was the actual fall of SCADA. On 30th July, the northern grid collapsed around 9:30 a.m., leading to a load loss of about 36,000 megawatt. The very next day, on 31st July, things got worse. 3 grids, northern grid, eastern grid, and northeastern grid, they failed together around 1 p.m. So because of overdrawal of power, transmission congestion, and the lack of timely corrective actions, the disturbance actually spread rapidly from one region to another and causing a complete collapse. So the result was around 620 million people, means millions of people, around 9% of world population, if we say, they were left without power, and it made it largest blackout in the history. So at that time, we were relying on the mainly SCADA system, and we have observed, or we have realized, that the grid operators had no real-time or wide area picture of how stress was building up across the regions. So that was the reason why we failed with the SCADA. So this incident actually became a turning point for the India's power sector, and it showed up that the traditional SCADA-based monitoring system is not enough for a large interconnected and dynamic grid. So that is why the country moved towards adopting the advanced time synchronized measurement system, what we call wide area monitoring system, WAMS. So before we dive into WAMS directly, it is important to understand how the idea of phasor or concept of phasor evolved and helped in development of today's wide area monitoring systems. So this is the very basic, or you can say fundamental, about the phasor or synchro phasor I am discussing here. You can see just a phasor we can define as a in a simple mathematical way as a complex number which can represent any sinusoidal signal like voltage or current. using a complex number. So if you look at the figure on the left side, you will see a vector that actually rotates counterclockwise with the angular frequency or angular velocity omega. And the projection of this rotating vector on the vertical axis gives you a sine wave. That is the waveform we see in time, this waveform. So the length of phasor, so this rotating vector is nothing but the phasor. So the length of phasor represents the amplitude of sinusoidal, means maximum value. And the angle of phasor with respect to a reference axis gives the phase value. Gives the phase value. Just a minute. So this length of the phasor, if you observe, this is actually giving the maximum value, and the angle of the phasor with respect to this axis, reference axis, this is actually the instantaneous angle of the sine waveform. Similarly, you can observe the projection on this vertical axis is actually giving the value, instantaneous value of sine waveform. As the time goes, this phasor, this actually rotates with the angular velocity omega, and at some time when the phasor is at this location, instantaneous angle will be some angle theta 1. If this is theta 0, this will be theta 1, and the instantaneous value of this signal will be this much. So in this way, we can realize the concept of phasor. So instead of dealing with continuous varying sinusoids in time, we actually represent them as a phasor or fixed vector in the frequency domain. So this makes the analysis of AC systems much simpler. But here, there is an important limitation that the phasor alone cannot be synchronized, or they can, phasor alone are not actually synchronized across the grids. For example, if I measure a phasor in Delhi and you measure another in Mumbai, our measurements are actually reference to our local clocks. So the phase angles cannot be compared directly because the reference time may be may be different due to the difference in the reference local clocks. So it means we need to measure the phasors with reference to a common clock, a reference clock, common reference clock. So this is the key issue when we try to analyze an interconnected grid. So to overcome this, engineers developed this concept of a synchronized phasor. Synchronized phasor, or you can say the synchro phasor. So you can observe synchro phasor is nothing but a phasor that is actually time stamped with a common reference clock, so that the phasor measured at different location, whether this is Delhi or Mumbai, can be compared directly. So these synchro phasors are measured using the device that we call PMUs, phasor measurement unit, which use the GPS signals to maintain the precise time alignment, or you can say to provide the common reference time at all the locations, at location A and location B, to the PMU. Okay. So so to understand the importance of synchronization, here we can observe, we can consider two substations, substation A and substation B. They are located far apart. So their voltage waveform look independent, and phasors are measured actually using the local clock in this case. So we have considered the phasors measured with reference to their local clock. So even a small clock drift between PMUs can lead to large measurement errors. For instance, PMU A might be 120 microsecond fast PMU-B might be 80 microseconds slow. So this creates an effective time skew of 200 microsecond. So now if we calculate the resulting phasor angle error, in this case, the phasor angle error will be 3.6 degree due to this effective time skew of 200 microsecond, considering the fundamental frequency of 50 Hertz. So this small timing error can cause a major power flow mismatch. In the example shown that the true power flow is about the 804 megawatt. If we are considering the true delta as 30 degree, then the measured delta, it may be 30 degree plus minus 3.6 degree. So if the true value of power flow is 804 megawatt, we may estimate the wrong value as 730 megawatt due to this time error. So this causes the overall error of 100%. Oh, sorry, 11%. Sorry, this is an 11% error purely because of a small timing inaccuracy. So precise time synchronization is absolutely critical for the VAMPs to function reliably. So that's why we utilize the GPS time tagged data, common reference signal, common reference time signal for the angle measurement. So now that we understand the idea of phasor, synchrophasor, let's now move to the system that brings everything together, the wide area monitoring system, VAMS. So VAMS is actually the integrated system that consists of PMUs, PDCs, communication links, control centers, and applications that provides a synchronized real-time wide area view of power grid. So this diagram shows the typical wide area monitoring system at different points in the grid. Generation, transmission, distribution, phasor measurement units are actually installed, and each PMU, phasor measurement unit, measures the voltage, current, frequency, and the rate of change of frequency, and it synchronizes these measurements using the GPS timing, GPS signal. So these PMUs send their data through high-speed communication links to a phasor data concentrator, PDC, usually located at the regional center or national center. The PDC collects the data from all PMUs, align them based on the time stamping, and sends the synchronized information to the central level, which is actually the state estimation and decision support system. So in some location you may observe there is micro PMUs. Micro PMUs also used. These are actually the smaller versions designed for the low voltage networks like distribution system or renewable integration points. So all this together form a real-time wide area view of the grid where every node is connected through the synchrophasor technology. So this is how the VAMs create the situational awareness across the large interconnected areas. So I already told that the wide area measurement system is integrated system that is having PMU, PDC, okay, everything. So I have discussed briefly about the PMU, PDC, function of PDC. Here we also require communication infrastructure that should be capable of exchanging the information with high speed and low latency. Okay, so for that purpose, we utilize the fiber optics ground wires in our power system, OPGW. Okay, similarly, once data reaches the PDC, it is forwarded to the control centers which operate at different levels. Different levels means state level, regional level, and national level. So each control center visualizes the synchrophasor data in real time, and by this grid operator can take the quick decisions है ना, quick decisions. They may analyze they may detect the oscillations, voltage instability problem, or any abnormal frequency patterns, and based on the analysis they take some corrective actions. So here I will discuss the India's journey towards the nationwide WAMS that began with a small pilot project carried out by the PGCIL between 2008 and 2010. The main objective was simple and practical. The pilot project, it was intended as a proof of concept to demonstrate whether the synchrophasor based monitoring could give real time synchronized visibility or not, okay, in Indian grid conditions. So in this pilot project, a total 14 PMUs were installed across the 3 regional grids, northern regional grid, western regional grid, and eastern region grid. So these units actually were placed at the strategical important 400 kV substations and inter-regional tie lines. So the this project completed in 2010, and the success of this pilot project provided the confidence to scale the idea nationally. So you can say it was the foundation of a wide area monitoring system in India. So by the success of this pilot project, the PGCIL, they have conceptualized a national program called Unified Real-Time Dynamic State Measurement project or URTDSM project. So the stated objective was to establish a nationwide real-time dynamic monitoring of the transmission grid for the Indian grid. So this URTDSM project, it was conceptualized into 2 phases, phase 1 and phase 2. So in phase 1, phase 1 actually it was initiated in 2013 and completed around 2020. So about 1186 PMUs were installed at roughly 351 substations covering 400 kV and above voltage levels. 34 PDCs were deployed, one at National Load Dispatch Center, regional 5 regional load dispatch center, and 28 at state level dispatch center. Dedicated optical ground wires, or you can say OPGW, communication network was provided for reliable low latency data transfer. So in this way, phase 1 integrated the synchrophasor data with the existing SCADA and EMS system, energy management system. So operator could use high-speed PMU data alongside the conventional data for improved observability. So in short, we can say phase 1 established the nation's foundational WMS backbone. So this is the about the URTDSM phase 2. So phase 2 actually focuses on widening and deepening the wide area measurement system coverage, and it actually added the additional PMUs as 220 kV as well as the 132 kV substations to provide the finer visibility. In phase 2, they have deployed the redundant PDCs for higher resiliency, integrate advanced WAMS applications such as dynamic state estimation, oscillation source localization, real-time angle stability monitoring, and predictive early warning systems. So phase 2 therefore moves WAMS from observability to analytics, and preemptive actions. So in summary, we can say this India actually moved from a pilot project of 14 PME to one of the largest national WAMS deployment in the world. So phase 1 laid the technical foundation, and phase 2 aims to expand the visibility, add the analytics, and enable the nationwide predictive capability. So URTDMS has fundamentally changed how the grid operators observe and respond to dynamic events. Sorry. Now I will also discuss something about the standards. Standard for the synchrophagers. IEEE and IEC have published standards that defines how synchrophagers should be measured, tested, and communicated. So these standards actually ensure the interoperability. Interoperability means the capability to communicate between the devices that are actually of different manufacturers. So these standards ensures the interoperability between the devices, and you can say the ensure or guarantee a certain level of accuracy under both the steady state as well as the dynamic conditions. So the history of standardization began with the IEEE standard 1344 in 1995. So this was later expanded into IEEE C37.7.118 2005. There they have defined about the phasors, frequency, and the rate of change of frequency. In 2011, the standard was split into two, C37.118.1 for measurement accuracy and C37.118.2 for communication protocols in 2024. Finally, so in this way, they have the standards has been evolved with the time. So according to this particular standard C37.118, they have defined the PMU as a device that actually produces the synchronized measurements of phasor, its amplitude and phase, frequency, rate of change of frequency from voltage and or current signals based on the common time source that typically is the one provided by the GPS, global positioning system. So this IEEE standard, they actually also define the error matrices to evaluate the accuracy of synchrophager measurements. The most important of these is the total vector error, or TV. We sometimes call it as a TV. So TV is actually essentially a you can say they actually compare the true theoretical phasor with the estimated phasor reported by the PMU at the same instant. So it combines both magnitude as well as the phase error into a single measure. So you can observe here this cap. This cap indicates the estimated value. So this is XR hat. This indicates the real value, real phasor value, estimated real phasor value. This is actually the true value. Hope you can see this. This is the estimated real part of the phasor from the PMU. This is the estimated imaginary part of phasor from PMU. And this is actually the true real part of the phasor. This is the true imaginary part of the phasor. Okay. So it combines both magnitude and the phase error, okay, as it is considering real as well as the imaginary part of phasors for calculating the error. So TVE, here you can observe this is the this is normalized also. Okay, but normalized also, but in sometimes we may observe that they have calculated the total vector error in terms of percentage. So for that purpose, they multiply it by the 100. So we can say this total vector error is actually the benchmark for determining whether a PMU is good enough for accurate synchrophasor reporting or measurement or not. So some of the other indices matrices that IEEE standard provides, it also provides the indices for calculating the frequency error as well as the rate of change of error. So this IEEE standard put limits on all the three error matrices, that is TVE, total vector error, frequency error, and rate of change of frequency error to ensure the that the PMUs are reliable, not only in steady state as well as during the dynamic system events or dynamic conditions. So this particular standard also specifies two performance classes of PMU, P class and M class. The P class, where P stands for the protection. These PMUs are actually meant for the protection and control applications. They are designed to give a very fast response, which is actually crucial for system protection and fault detection. So mainly this type of PMU, this type of class, P class PMU, we utilize for the protection and the control applications. Obviously, for achieving the fast response, they are allowed to compromise with the accuracy up to a certain extent only. Next, the M class. M stands for the measurement. So these are actually intended for detailed monitoring and analysis purpose in the system. They focus on high accuracy rather than the speed. Whereas P class, they actually focus on the speed compared to your M class. Now let us see how PMUs are tested under different influence quantities like the frequency variation, voltage current range, etc. So the IEEE actually sets the limit on how much error a PMU can have under the standard test condition, and the error is measured in terms of total vector error. Total vector error. So here you can see this particular standard defines this total vector error limit for both the classes P class and M class. For different influence quantity like signal frequency deviation, voltage current range, and phase angle. So if you observe for the P class PMU, the maximum total vector error must remain within this limit of 1% when the frequency changes within the range of plus minus 2 hertz. Okay. So if the frequency is 50 hertz, the fundamental frequency is for 50 hertz, and at any moment of time, the frequency of the signal is deviating by the plus minus 2 hertz, or you can say the signal is actually in between 48 to 52 hertz, then in such case also P class PMU must report the phasors with maximum of 1% total vector error. Similarly, they have defined for the M class PMU. For M class PMU is intended for the monitoring and detailed analysis purpose in this system. So in that case also, they have defined the maximum total vector error 1%, but they have defined this corresponding to the reporting rate. Means how faster is your PMU is reporting the data. If they are reporting the data with the data reporting rate of or data reporting rate 10 frames per second, then for plus minus 2 hertz frequency deviation, it must sustain or it must provide the phasor, estimate the phasor with maximum of total vector error. If the data reporting rate is in between 10 to 25 frames per second, then the frequency, then the range of frequency deviation is plus minus data reporting rate by 5. Let's say if the data reporting rate is 20, then the frequency may deviate for plus minus 4 hertz, and the total vector error should remain within this 1% total vector error limit. So in this way, they have defined the allowable total vector error limit in respect of influence deviation in the influence quantities. Similarly, you can observe for the voltage and current. For the voltage, you can observe if the voltage changes or deviates within the range 80% to 120% of the rated, then the total vector error should remain within the 1% limit. Whereas for M class, they have given the limit of 1%, even if the signal magnitude is actually voltage signal magnitude varies from 10% to 120%. Similarly, for current, they have defined if the current signal magnitude vary from 10% to 200%, then also it should calculate the phasor with the accuracy or with the maximum total vector error of 1%. Similarly, for M class. Okay. They have also shown the phase angle variation. So if your fundamental frequency is F0, okay, let's say 50 hertz, and your actual frequency is Fin, let's say your actual frequency is 50 hertz, and means your fundamental frequency is 50 hertz, and at some moment of time, the frequency of signal changed to 49.8 hertz, 80 hertz. It means the actual difference between the fundamental frequency and actual frequency, it is 0.2 hertz. Then also, whether the actual limit is 0.25 hertz, it may vary up to 49.75 hertz. So even the main signal is not of 50 hertz, your PMU must measure the phasor with maximum total vector error of 1%. Okay. It is like when we actually measure the phase angle, if this is the signal, if you see, as per the fundamental time or rated frequency, the time period is actually T, which is actually of 20 milliseconds. So if you see, this is the assumption that the signal is of rated frequency, but in practice, the signal frequency may deviate. So in this case, if you observe, theta is actually 0 degree, but due to the shift in the frequency in second cycle, you may observe this is the angle theta 1. Similarly, after one more cycle of 20 millisecond, you may observe now the angle is theta 2. So in this way, you are actually, your phase angle, measured phase angle is actually changing with respect to time due to the deviation in the frequency of signal. So in such conditions also, they have forced to comply with the requirement of maximum total vector error of 1%. Similarly for M class. So in this way, they have defined the steady state measurement requirements. So till now we have discussed about the steady state measurement requirements according to this particular standard. Now we should see the requirement for the dynamic conditions as per this particular standard. So obviously this our requirement is this, that the PMU must report the phasors accurately even in the dynamic conditions, because in reality power system experience dynamic conditions like oscillations, swings, or some disturbances. So to test if a PMU can still track correctly, can measure the phasors correctly, the IEEE standard introduces the dynamic compliance test. So these tests use actually the amplitude modulation and the phase modulation of input signal, and check whether the PMU can still track the slow changes or not. Do its phasor frequency and rate of change of frequency stay within the required error limits or not? Obviously, the error limits compared to the steady state is high. Like in steady state, we have observed this limit was 1%, whereas in case of dynamic compliance limits, this limit is actually 3%, depending on the class. So to check the requirement, dynamic compliance requirements, they actually modulate the signal. Let's say this is the ABC signal, A phase signal, B phase signal. So here you can observe they have actually modulated the magnitude as well as the phase, and then they check the PMU whether it is able to measure the phasors accurately or not. So depending on the modulation level, they have defined the total vector error for P class as well as the M class. So here you can observe that the maximum total vector error allowed in this dynamic conditions, it is around 3%. Compared to steady state, it is high. So in a steady state, the IEEE standard, they forced to comply with the maximum total vector error of 1%, whereas in this case of dynamic conditions, they forced to have the maximum total vector error less than the 3%. So this is all about for today's lecture. So if you wish to interact with me or to ask anything about the about this particular session, you are free to ask. I will say I'm not expert. I have just shared the knowledge or information I have.
So, dear participants, if you have any questions, you may unmute yourself and may ask. It's very timely topic, wide area monitoring system, because this is under implementation across India.
Yes, sir. Actually, I choose this area because currently I am working on this area. I am also learning. So I thought of sharing you with my knowledge and the information what I got during these days. So if you wish to ask or if you wish to interact later also, you can interact with me with my email ID. You can write me anytime. I will be happy to respond you all.
So please share your email ID here.
Yes, sir.
So that in the chat box, so that
Just